This is OPI Structure Part 5, Access Query.
Building a query in Microsoft Access. We're using the Access Graphical Query Editor in this example. Select the Access Create ribbon, and in the Queries section, select Query Design. Access pops up a dialog box for you to select queries, tables, or both to participate in the query you're building. This first query selects linked tables, so click to select two tables. For PowerOpI, those will be the range alloc and range BOM tables linked in from Excel. For later queries implementing the PowerOpI structure, you would select the query that joins the previous structured table in the PowerOpI stack, and also select the next Excel structured table to be joined in that sequence. Select the tables to join, click OK, and the tables or queries selected will show in the Graphical Query Editor. Each table lists all its fields, and each table also shows a star symbol to select all fields. Looking below the graphical table symbols in the Query Editor is a grid area to design the query from fields in the selected tables. For PowerOpI, drag the star symbols down, one table to each column, to the row labeled Field. Star means all fields in this table. A big data application wouldn't select star because query results could become huge, but PowerOpI datasets are comparatively small, and there's an advantage to selecting all fields in the query. Selecting star allows you to add, delete, and reorder fields in the Excel structured tables to which these Microsoft Access tables are linked. Excel will be your user interface to the database. That updated table structure will show up automatically in Access when this query is refreshed, and therefore also in the query results since you selected star for all fields. That's enormously useful for PowerOpI, where you're working on a project that's quivering like a big bowl of jello, changing every day. Changing fields to help build structured keys or to add characteristics of system elements or operations is done quite frequently. Select star in Access makes this nice and transparent. Both Power Query and SQL Server behave differently than Access when fields are added, deleted, or moved. There's a discussion of that in a later page in this module. Now join the tables. Determine which table drives the query. That's shown in the example query structure. Put that table on the left in the Graphical Query Editor. Determine which fields link the two tables. For PowerOpI, that's almost always one of the three join structured keys shown earlier: item ID key, item rev key, or item task key. The key for the tables in the PowerOpI example query structure figure shows which field is used above each query box. To join, drag from the Join field in the left table over to the Join field in the right table. The line between them graphically indicates the join. Then set the join type. Right-click the graphical line connecting the join fields in the two tables. In the right-click context menu, select Join Properties. For practically all PowerOpI joins, we want a left outer join, which is the second item. Select Item 2, which is Include all records from left table name and only those records from right table name. Access puts the table names in there properly, where joined fields are equal. I'll show a graphical example explaining left outer join shortly. On OK, the Join Properties dialog closes, and an arrowhead is shown in the graphical line showing the join. You can check the query result by clicking the View button. If you want to see the SQL created by Access for the graphical query design, use the View button to select SQL View to view or edit SQL. Right-click the tab at the top of the design page to close the query. Name the query if asked. I always name a query with a lowercase q prefix. We almost always use a left outer join. So what is a left outer join and why do we use it? Let's step through a join and see what it does. Two SQL tables at left and a query results at right that looks a lot like a table. The top table is named Table Alloc and describes allocation of equipment to organizations. The equipment is named by field element name. The equipment type is specified element rev ID, and the organization, use, and rack to install it in are in fields org, use, and rack. The bottom table is named Table BOM and describes what elements are needed in order to build each type of equipment. The equipment type is specified by field element rev ID, and the subelement is named and specified by field subelement name and subelement rev ID. The quantity of each subelement needed for one element rev ID is specified by field subelement quantity. The field element rev ID was designed to be used as a join key in each table. And notice the query is shown in SQL at bottom right. The first record in table alloc is highlighted and specifies that a chassis rev ID-A is allocated as specified in field element rev ID. So we want to look up from table BOM what kind of subassembly units have to be built to deliver that and how many of each. The value chassis rev ID-A in field element rev ID in the first record of table alloc matches the element rev ID value in the records highlighted in table BOM. So we are going to need 3 subelements named in the subelement name field and specified by the subelement rev ID field in quantity specified by those fields for the equipment allocated in the first record of table alloc. This is an explosion. One input allocation record results in 3 query result records, one for each subelement needed to build the allocated chassis rev ID-A unit. So the query result for the first table alloc record will result in 3 records in the query result, which is 1 record for each of the 3 matching records in table BOM. The query is designed to take all fields from table alloc and all fields from table BOM for matching records, and that's what's shown in the first 3 records in the query result. For the second record in table alloc, the element rev ID value other rev ID matches 1 record in table BOM, so the query result contains 1 more record containing all the fields from the table alloc record and all the fields of the matching other rev ID record in table BOM. The third table alloc record again matches the same 3 chassis rev ID-A records in table BOM, so the query result contains 3 more records, each with the field values from that third table alloc record and the matching field values for chassis rev ID-A in table BOM. The fourth record in table alloc matches 2 records in table BOM, so the query result adds 2 records with the field names of the fourth record of table alloc and field values of each of the 2 matching records from table BOM. The fifth record of table alloc matches no record in table BOM. We don't want to forget that we allocated that 5th piece of equipment. We'd rather show the item in the query result than be able to flag an error somewhere down the line that build information needs to be added. So we use a left outer join. Where no record match is found, a record is created in the query result, populating selected query result fields with values selected from the left table, and leaving blank values for fields selected from the right table. You can do calculations in SQL in the queries. I do most in-table calculations in Excel because that's easy, and use the database to aggregate fields as tables are joined and to explode records. But there are some calculations that you must do in the join because you don't have enough information in the tables before the join is executed. Let's say you're allocating a chassis that contains 4 SSD plugins. You allocate 1 chassis, you have to buy the 4 SSDs. Extended quantities of SSDs in a chassis is 4. But if you allocate 5 chassis, you have to allocate 5 times 4 equals 20 SSDs. So extended quantity of SSDs in this instance is 5 allocated chassis is 5 times 4 equals 20. Until you do the join of the allocation table with the BOM, you haven't got enough information to work that out, unless you replicate the join in an Excel calculation, which would be hard. I think DAX can do that. But let's do it in SQL for now. In table alloc, there will be a field for alloc quantity for the chassis or some other element, and in table BOM there will be a field for subassembly quantity X of SSD or some other subassembly. There will also be a subassembly cost X for each subassembly. You'll have equivalent fields for all these I've created names for, and you should design your Excel tables to contain these fields. So you'll calculate 2 new fields in the join, alloc quantity X and alloc cost X, when those tables are joined. You use the Access Expression Builder. As you design the query in the Access Graphical Query Editor, right-click a new query column and select Build. A dialog pops up. One of the expression elements available in the leftmost pane will be a directory of queries that contains the query we're building now. Select that query and then select fields from it by double-clicking alloc quantity and sub-assembly quantity ext or equivalent fields. Edit the expression in the Expression Builder top frame. It should be something like alloc quantity ext colon bracketed alloc quantity times bracketed sub-se quantity ext close bracket. It's named at the start of the expression as shown in the illustration. Also, create a similar expression for alloc cost ext colon alloc quantity in brackets times bracketed sub-se cost ext. Click OK to finish. When you're done with the query, right-click its tab at the top of the Query Editor panel and save it. Remember to name it and use a prefix Q. By the way, in the slide showing the SQL query for all tables, notice how there are calculations done in the Select clause to handle these issues.
To use a query result as a pivot source via an Excel data connection, close Microsoft Access and open Excel. From Excel ribbon Insert, Table section, Pivot Table button, click Use an External Source, then click Choose Connection. In the Connection dialog, click the Browse for More button and browse to the Microsoft Access database file. The Select Table dialog pops up. Select the query to use as the source for the pivot. You'll return to Excel to finish the pivot. Beware of Microsoft grouping dates. In most cases, you don't want them grouped. If you need to ungroup them, right-click a date field in the Pivot Table field list at the right of the Pivot Table Editor and choose Ungroup. We used the Access Graphical Query Editor in the last example. You might prefer to write SQL, and in fact that's a good idea for complex queries. We're using the Graphical Query Editor because we're just doing two table queries and stacking queries because that's easy in Access and works fine for PowerOpI type applications. You won't be able to do that in SQL Server. In the Access Graphical Query Editor, use the View button at the far left to select SQL View. The View button is confusing. It shows some other view that can be selected, but its drop-down can always be used to select among SQL View, Design View, and Datasheet View when a query is open. Now you can type or paste in SQL. We're not teaching SQL here, but I'll show a working path with a real query, and learning SQL is up to you. This SQL represents a structure like the graphical structure shown earlier for use in a PowerOpI application, and joins all of the linked tables in a single query. Right-click and save the query and name it if needed. I'd use a lowercase q as a prefix for the name. Notice that in the SQL, field names are enclosed in brackets, and also that SQL expression carefully uses parentheses and ends with a semicolon. Access requires these syntax points. In fact, the SQL shown was created by Access. SQL Server is much more forgiving on the fine points of SQL syntax. Here is the PowerOpI query as used in Access in bigger typeface so you can read it. There's more discussion of queries like this in other scenarios with Access and SQL Server in the SQL Server module in this channel. This OPI structure sequence continues in OPI structure part 6, Power Query.